Question 1. Use Euler's method to find 5 new points that will help approximate the solution to the differential equation y prime equals x plus 3y given that y of 0 equals 3 and h equals 0.1. In Euler's method, remember, h means the step size, so that's how far we'll go each time. We're given right here that we're going to start with the point 0, 3. We know we're going to go up by 0.1 each time, and we're asked to find 5 new points. So we'll go to 0.5. And the formula we use to find the y values for these points is y equals y1 plus mh. So to find our first one, we need to plug in the y value we currently have, which is 3. We need to find the slope we currently have. To do that, we take this point 0, 3 and plug it into the differential equation. So I plug 0 in for x and I plug 3 in for y, and the slope would be 9. And then I plug 0.1 in for h. So 3 plus 9 times 0.1 gives you 3.9. Okay, next step, we plug in the new y value, which is 3.9, and we find the new slope. So now we take 0.1 and 3.9 and plug it in right there. So let's see what we get. 0.1, try that again, 0.1 plus 3 times 3.9, and we get a slope of 11.8. So 11.8 times 0.1 plus 3.9. So our new y value is 5.08. So now we repeat the process. We put in the new y value, 5.08. We find the new slope, which is going to be 0.2 plus 3 times 5.08, which is 15.44. And we multiply that by our h, which is 0.1. So multiply our slope by 0.1 and add 5.08, giving us a total of 6.624. Okay, then we do the process again. We put in the new y value, 6.624 for y1. We find our new slope, which is going to be 0.3 plus 3 times 6.624. That's our new slope. We multiply that by 0.1 and add plus 6.624. Get our new y value. Alright, so 8.6412. I'm going to go ahead and fill in the rest of that step just so it's all written up here. You can always pause and look at the work again if you need to. See, 20.172 was the slope. Okay, and then one last time we have to do this. Plug in the newest y value, 8.6412. Find the slope, which is 0.4 plus 8.6412 times 3. Plugging it into the differential equation, I get 26 point, let's see, make sure I plug that in right. Yeah, it looks right. 26.3236 times the 0.1, and then add 8.6412. So let me try that again, miss the 6. Okay, there we go. And our last one should be 11.27356. Okay, so those are the 5 new points right there. And again, the idea with Euler's method is if we plotted these points, it would give us an estimate of what the answer to the differential equation would look like. Question 2. Given the logistic equation dy over dt equals y times 1 minus y over 40, answer the following questions. What is the carrying capacity for the equation? The carrying capacity is whatever number you would plug into this y, the one inside the parentheses, that would make what's inside the parentheses turn into 0. In other words, if you need to solve for it, you could do 1 minus y over 40 equals 0. So then you would add y over 40 to both sides, multiply both sides by 40, and you get 40 equals y. That is the carrying capacity, whatever number you would plug in for y that would make what's inside the parentheses 0. Part B asks what the limit as n approaches infinity, so that should actually be t approaches infinity, my mistake there. Limit as t approaches infinity of y of t. Well, if you look, we don't have y of t, we have its derivative. But the limit as the original goes to infinity is the same thing as the carrying capacity. Part C, at what value of y will the equation be growing the fastest? Well, it turns out with logistic differential equations, it's just those, that the equation is growing the fastest at the point of inflection, and that both of those things happen at half the carrying capacity. So since the carrying capacity is 40, it's going to happen at 20. Number 3. The number of fruit flies increases according to the law of exponential growth. As soon as I see exponential growth, I know I'm dealing with this equation. If initially there are 25 fruit flies, meaning my C is 25, and after 8 hours, meaning my time is 8, there are now 75, I put that here. Find the number of fruit flies after 15 hours. Okay, so looking at what I've given, when I plug that in, I can solve for k. I'm going to divide both sides by 25, take the natural log of both sides, and then divide by 8. So I know k is equal to the natural log of 3 over 8. For now, I'm going to leave it that way. Let me write that a little bit differently. There we go. The 8's outside the natural log. I wanted to make sure that was clear. You can plug that in and get the decimal, but I'm going to leave it that way just so it stays exact. So my regular equation then should look like this. And they want to know how many fruit flies there will be in 15 hours. So all I do is plug in 15 for t and see what that gives me. So 25 times e raised to the natural log of 3 over 8 times 15. I get 196.129. A certain type of radioactive element has a half-life of 500 years. What percentage of the sample is left after 800 years? Okay, so we have y equals ce to the kt. We know initially there's 100% of it, so I'm going to put 100 in for c. And it wants to know what percentage is left after 800 years. So I know my time is 800 years. Now if you remember, there's a very specific formula for k. K is equal to the natural log of 1/2 over the half-life. If you remember that formula, then you can immediately plug in, and move that 800 over, natural log of 1/2 over 500 times 800. But if you don't, and I'm not going to be putting it on this test, you're going to have to just remember it, then there is a way you can solve for it. Okay, so I'm going to show you real briefly down here how you can solve for it. We know that the half-life is 500 years, meaning that after 500 years, we will have gone from 100% to 50%, because it cuts it in half. Well, if you divide both sides by 100, you get 1/2 equals e to the k times 500. Then take the natural log of both sides, and you get k times 500. And then divide both sides by 500, and hopefully you see exactly where that formula for k comes from when it comes to exponential decay with radioactive elements. So that is also one way you can solve for k if you forget this formula right here. Okay, but we have all the information we need, so we can just plug that in the calculator and solve for what percentage is left. Do 100 times e raised to the natural log of 1/2 over 500 times 800. And we get 32.988% if we're rounding. So 32.988% would be left. Alright, we'll do one more and then we'll switch to video 2 after that. Question 5. In 2000, the population of a town was 150,000. In 1995, it was 135,000. Assuming the population increases constantly at a continuous rate proportional to the existing population, estimate the population of the town in 2005. Okay, the earliest time we have is 1995, so I'm going to treat that as my initial time, and that means that 135,000 will be my C. I'm again dealing with exponential growth and decay, so I use this equation. I know my C is 135,000. And I know that 5 years later, in the year 2000, we were up to 150,000 people. So let's divide both sides by 135,000. So that gives us 150 over 135. I'll plug this in a second. Then we take the natural log of both sides. And then we'll need to divide by 5. So our K is going to be the natural log of 150 over 135, all divided by 5. Make sure the divided by 5 is outside the natural log. So it's 0.021. But I want to use that exactly, so I'm going to store this. In fact, I'll just use K, so do alpha K. And then that way your calculator saves that number for you as K. But we know it's about 0.021. So that's all I'll write when I'm doing my work now. So it wants to know what the population would be in 2005, which would be 10 years later. So again, my initial amount is 135,000. I already know my K. I'll just write it as K. We can use it in the calculator. It's about 0.021. And my time is 10 years later. So I can plug this in and estimate what the population would be in 2005. 135,000 times E raised to the K times 10. And it's 166,666 people. Or rounding to the nearest person, we can do 667. It's fine on living things if you want to just round to the nearest whole number, since you can't really have just pieces of living things, at least not still be alive. The rest of this will be in video 2.